Hey guys, in today's video, I'm going to be implementing a linked list in Dart. Um, if you're not familiar with Dart, there's no need to worry or fret. That is a really simple programming language, and if you've written code in Java or JavaScript or any modern programming language, you should be able to pick up the concepts easily and apply them in a language of your choice. Um, all right, so you probably heard about linked list either from um, people who are freaks about interviews. Let's say you're trying to interview with big tech companies. They don't have to be big tech companies, which is just the interesting part. If you have touched some part of lead code, then you've probably seen some linked lists related questions. And so I'm going to show you how to implement one. I'm not going to go into the details of some of the use cases or some very interesting problems that you can solve using a linked list data structure. I'll just show you how you can implement this data structure and give a very slight contrast between it and an array, and to see how linked list can be used in place of an array and why in some programming languages their list definitions, the data type list or array list or whatever, basically implementation of linked list. And you find out the reasons in this video. All right, so this is also the first video that I'm going to be uploading on YouTube. So hooray. Let's get right into it. Okay, so an array is, I have no idea why I can't zoom into this. There we go. An array is basically a contiguous, it's a chunk of memory where items are placed in contiguous blocks. And what that means is just one after the other, right after the next one within that same block of memory. So what this means is um, for you to define an array, you need to know how much memory that you're going to need to take out from your computer or your machine. And then in that chunk of memory, you split it into partitions where you put the elements of your array into each of those partitions. So this structure makes it very easy for you to find the elements of your array by index, because and this operation happens in constant time because the elements are in different partitions in that array that are next to each other. So you basically do some bit shifting operations from one memory address to retrieve the next memory address, and yeah, that's that's why you get it in constant time. The downside of an array because of this is that if you have something that is a growable list or something that's not a fixed size of element or a fixed number of elements, then using an array to implement something like that becomes very expensive, because what you're making your computer do every time you add a new element or remove an element from your array is, in the case where you add a new element, your computer has to recompute your program has to recompute the amount of memory it needs, find that chunk of memory. So you're basically killing off this chunk of memory, find another chunk of memory, and then create partitions and copy in your elements into those partitions in this newer chunk of memory. And if you remove, they're doing the same thing. You find another chunk of memory that fits how many elements that you now have, then copy your new elements into those partitions that you've created in this memory block or piece of memory that you have. So adding and removing items from an array is really expensive because you're doing a lot of copy operations and moving things back and forth um, within this block of memory that you've allocated for your the elements in your array, right? But retrieving the elements happen in constant time. So it makes sense to use an array where the elements don't change. So they're a fixed number of elements. And yeah, you don't add to them, you don't remove from them. That's why it makes sense to use an array. But when you have a collection of items that you want to be able to add to or remove from or load dynamically. Let's say you're querying your server to retrieve a list of products. You have no idea how many products there are going to be. Or you're probably querying your server to get the list of products in your cart. You could add to the cart, you could remove from the cart. So this is an interesting place where you need a substitute to an array. And that substitute can be a linked list. The way the linked list works that is different from an array is that the linked list does not create a block of memory where the items in that list are contiguous or next to each other, just right after themselves. How the linked list works is by referencing, basically. So it works by pointing memory locations to each other. So you have a link from a certain memory location, which is probably where the first item is, to the next, and to wherever else you have items in memory. So basically, you can have memory locations that are not contiguous, scattered all over the place, randomly picked, if you may, um, where you can store one item from your list, but then point to another memory location where you have the next item in your list, and then point to another memory location where you have the next item in your list. So that's how the linked list works, and how it's different from an array. In an array, you need a certain block of memory, and the addresses are contiguous. So you can do some bit operations on the first address to retrieve the next address and the next address and the next address. But in a linked list, they are not necessarily contiguous. And so to find the next memory location, you need to keep the reference of that memory location in the previous node. Okay, so I've mentioned node, and I should say what that is in the context of the linked list. So basically, a node is that specific chunk of memory or piece of memory that contains your item, the element, and then it also contains a reference to the next node. So the node is basically an encapsulation of the data, the item, the element, and a reference to the next one that contains something. So at some point in your linked list, you get to a node that contains an element but points to nothing, which indicates that you're at the end of your linked list. It points to nothing. So there's no reference, there's no next pointer, if you will. And this is how the linked list works. This is how the linked list works. And so you can use this to solve the problem of having to like making your array growable. Remember the problem with creating a different chunk of memory that can accommodate the number of items that you now have, and then copying over all the elements from your old array into the new one. With the linked list, you don't have to do all of that. All you're doing is appending a new node to the last node in the list. If you're just removing the node from the list, and then resolving the references so that the references between the nodes that are still remaining in the list, so that it is still intact. All right, so yeah, that's the basic explanation of how the linked list works. We're going to see some code and implement it basically in code right now. So here I have an empty file, and I'm going to create two objects, node, and then the linked list itself. If you remember from my explanation, the node is an encapsulation of the item in your the item or the element and a pointer or a reference to the next node. So these are going to be the properties of this guy node. So we need I'm going to make use of generics here to make life easy. I will call this data, and then we need another pointer to the next node. So I'll create a constructor for this. So this pointer could be null. Where it is null is where the node doesn't have any next reference. So it means you're at the end of the linked list. That's where the next pointer or reference is null. Otherwise, it won't be null. Every node has to have an element or item in it or data. So I'll make this required. And yeah, this is null. So this is our node. This is our node class. Now down to the linked list. Back to this illustration, the linked list always begins with a node and then forms a chain of references pointing from that first node to other nodes in the list. So this first node is typically called the roots node or the head. They mean the same thing. In here, I'm going to call it head. And this is going to initially be null, meaning when this linked list is created, there will be no node in it. Yeah, no node, meaning there's no item in this list at first. And then when you start inserting items into this linked list, then we start creating the nodes and start creating the chains of references between them. Okay, so they're going to be three insert methods in our linked list. We're going to have insert at the beginning, which is going to add a new node at the beginning. So if we are to insert the at the beginning here, this is what it would look like. We're going to add another node. Probably call this node 0. Yeah, this is what insert at the beginning would look like. So you're making that new node the new head or the new roots, and then you're creating you're pointing it to what used to be the head or the roots. We're also going to have, I should highlight this here so that we don't miss it. So we have the insert at the beginning, insert at end, and insert at position. Okay, so how insert at end would work is we have to transverse this linked list and get to the last node, and then add a new node at the end of it, just like so. If I could make this smaller. Okay, I'm feeling lazy, so I'm just going to copy this and name this node D, and this will be insert at end. And we also have the insert at position. Now this would require you to provide an index number where you want to insert your new item, and it will work in 3 different ways. So if that index is 0, then you're basically performing the insert at beginning operation where you're creating a new node at the top at the beginning of your linked list. The new node becomes the new root or the head, and then you're pointing that new node to what used to be the previous head. So it would maintain the same chain of references. If the index that is passed to insert at position is the length of the linked list or -1, you might like the sound of -1 if you're coming from a Python background, which is a very nice syntactic sugar for adding to the end of the list. So we should implement that here. Then it should basically be performing insert at end. Then if it's any other number, if it's any other positive integer between 0 and the length of the linked list, then what it would mean is that we're going to be breaking off one of these chains and inserting a node in between. So let's say we want to insert a node, want to insert node E at position 2. And this is 0 indexed. So this is 0, this is index 0, index 1, index 2. This is where we want to insert the new node. This is not by any means a replacement. So we're not replacing node B. We're basically in creating, you're basically going to be pointing node A to the new node E, and then pointing node E to node B, right? So we're not breaking off, we're going to be temporarily breaking off the chain between A and B, and then filling that space with node E. So what that would look like is this, where, give me a second, where we are breaking this off, right? And then we add node E, and include a reference, this. Okay, I think I have messed with the diagram. So let's do that again. Hold this off, add the new node E, and then point node E to the rest of the lists. And this is what insert at position will look like, depending on what that index is, what the position that you're trying to insert a new node is, right? So this entire structure that contains your nodes and the chain of references between them is what you call the linked list. All right. So we're going to try to implement all of these things that I've just described in code, and see how that goes. Okay, so remember, we need a root node or a head, which is going to be the first node that in our linked list, from where we can make the reference to all other nodes, right? So here I'm just going to call that head, and this is going to be nullable because at first it's just going to be empty. The linked list will be empty. There will be no item in there. Okay, so I'm going to create those methods, and then we can get to implementing them. So insert at beginning will require us to input some kind of data. So internally, we'll create the node and the pointers, the references. The user only has to insert data, and then we'll handle all of the internals of the linked list. You can choose to implement this differently, but this is how I'm choosing to do it at the moment. So insert at end, and insert at position. So instead of at position is a little different because it requires you to enter the index where the position where you want to insert that. So I think we should, yeah, let's just call this position, then the data you want to insert, right? It will make sense to override the toString method. So we can, for now, I'll make it return this. But later we are going to implement this so that we can um, go through all of the elements in our linked list and output them in some kind of readable list type format, right? All right, so we have the head, which is at this point null. It could be non-null later on in the life cycle of this object. We're going to go ahead and start with the insert at beginning, which is very straightforward. So there are two things that we should check for. If the head is null and we're trying to insert at beginning, then the insert will just set the head, right? Let's go back to here. From our diagram, we already have some nodes. I'm going to take out the node E. And then bring this all the way back. And take this out as well. Okay, so this is a linked list that already has a root node. So, and that was why my example of inserting node 0 was the way it was. If the linked list has no element in it at all, and you're trying to insert at the end or at the beginning, then you're basically setting the head. You're basically, you're basically setting the head. So if head is null, all we want to do is set head to, okay, we need to create our node. So I'm going to do that now. And set head to new node, and that's all. Otherwise, what we want to do here is point new node, make new node the head, right? So we'll be resetting the head, make new node, this object called new node, the head, and then make it point to what used to be the head. So I'm just going to say old head is head, and then head becomes new node, right? And head.next is the old head. Okay, so I have to and be conditionally assessed, yada yada yada, right? Oh, because it's final. Okay, so let's make this late. This can be final. And this is just because I don't want to create a setter here. And that's why I'm making this late. And yeah, there we have it. There we have insert at the beginning. Insert at end will work exactly the same for this first case where the head is null, but to be different for when the head is not null. So I'm just going to go ahead and copy this exact same thing for insert at end. When the head is not null and we're trying to insert at the end, what we want to do is go from the head through all of these chains of references all the way to the last node, and then create a new entry, create a new chain pointing to the new node, This is what we want to do with inserts at end. Right. So to do this, we're going to have to iterate, do some transversal. That's a basic while loop. We can do this with a while loop, and walk down this chain of references until we get to a point where there are no more chains of references. So that's an indication that we are at the last node in our linked list. And then when we retrieve that last node, we can point that last node to the new node, which would then become the last node in our linked list. Okay, so I had some microphone accident. All right, so let's go ahead and implement what I've just described. I'm going to, so since we're going to move from the head all the way to the last node, okay, this is what I'm thinking right now. And in a moment, it's going to make sense. Okay, yeah, we know it's not null. While last node dot next is not equal to null. Last node equals last node dot next. This should give us yeah, this should walk down this chain of references until it gets to the last node, and then it will set it in this object called last node. And then we can point last node to our newly created node that right up here. And this would, excuse me, this would do the insertion at the end. Just like that. Okay. So we've learned how to walk down the chain of references. So we can go from node A to node B to node C, all the way down to the last node in our list. So what this means is this is the perfect time for us to be able to implement the toString override so that we can print the elements in our list and make sure that insert at beginning and insert at end works before we implement insert at position. All right. So how that would look like here is I'm going to create a variable and yeah. So we're going to do this same kind of iteration. Well, I'm just going to change things up here. So we really don't care about we really don't care about. Okay, so we do have to set the current node, but at the same time we are updating results and we're retrieving the data from that node. Current node dot data. Current dot data. Right. And include a comma. So at the end, what this will do is add all the data for nodes for all the nodes except the last node, because this while loop will stop, will terminate when the current dot next is null, right? And that would be for the node before the last node. So to set the last node, but we'll not have the chance to re-execute and append this result, right? So we have to do this same thing outside of the while loop just once to be able to capture the one for the last node. Okay, I'm going to create a new file here. I'm sorry. Let's call this, yeah, main.dart. And use my linked list. Okay, so I'm going to print this first of all, print list, and we should expect to see just an empty list with the square brackets. No check operator use and no value. Interesting. Oh, okay. All right. Yeah, here's the problem. So remember how the head could be null, and the head is exactly null right here because this list is empty. But in our toString method, we are assuming the head is not null, and we are doing some kind of force unwrap on that null value. And that's why we have this null checkup, this null exception, right? So we have to add another case for when this is actually null, and return the empty representation of this, the empty state representation of the linked list, right? So if head is null, then just want to return this. And so if we run this again, yeah, we should see an empty list. Okay, so let's go ahead and add insert at beginning. Let's try insert at beginning. And I'm just going to insert one at beginning and then print this list. So we can see one. I'm going to insert another number 2 at the beginning, and we should see a list containing 2 and 1 because, 2 is pushed to the beginning again. Right. So the next thing I'm going to test is insert at end to make sure that works as well. And I'll be inserting 9. So our list should be 2, 1, and 9 this time. Yeah, that works. We'll insert 6 at end, and our list should be 2, 1, 9, 6 at when we print. All right. Just to make sure that we're not mistaken, I will insert 5 at the beginning again, and this should change. This structure should change to 5, 2, 1, 9, 6. Fingers crossed. Yay, that works. Okay, so insert at beginning, insert at end work perfectly. They work fine. Now we have to implement insert at position. Okay. First we create a new node, and then we have to make sure that the position you're trying to insert this data or this element is valid. And if it isn't, then we throw some kind of exception. One way to keep track of that is to keep track of the length of your linked list. You can find the length of your linked list by walking down the chain of references, but that's going to be expensive if you have to do this while loop. That's big O of n being the size of your list every time that you have to check for the length of the list. So an easy way to keep it to constant time is to have you're basically going to take up memory. So you're going to have an integer variable or property of your linked list class that will increment whenever you insert at beginning or at end or at position, right? And then in the insert at position method, we can do that quick check of whether the position is within that bound, with if it's lower than or equal to the length of the list at the time, right? Actually, we need it to be lower than, but let's see. So I'm going to create and set it to 0 and expose a getter to this. Excuse me. I feel quite parched. Right, so when we insert, we increase this length by 1. And that happens also at insert at end. Right. So if we go back here to our playground and also print list.length, we should get an idea of, we should see the right length printed out. So I'm going to print the same thing before we do all of the inserts. And we should see that the length will be 0. Yeah, the length is 0. And after inserting, we have inserted 5 items. The length of this list should be 5. Right, it is 5. And this length, we don't have to recompute it whenever we call this getter, which is the fun part. So when you're trying to insert that position, because this is 0 indexed, we're always, the valid positions are going to be between 0 and the length minus 1, right? So yeah, the valid positions that you could have are going to be 0 all the way to, so it's a range all the way to length minus 1, which is whatever the current length is minus 1. We also talked about including support for just minus 1, which will be syntactic sugar to represent length minus 1. I just like this because I wrote Python for a while, and this just grew on me. All right. So here we first of all check that the position is in the right range that we expect it to be in before we try to do any insertion. Okay, if position, so we know what the range is supposed to be, 0 and length minus 1. So the position can either be greater than equal to 0, less than equal to length minus 1, or -1. Those are the only allowed values. Position is greater than okay, so to find the values that don't conform, I'm going to flip the condition that I've just expressed. So the values that won't conform would be values that are less than 0, but not -1. You know what? I think we should take out the -1 for now. Yeah. Let's keep this as simple as it could possibly be. So the values that won't conform be values that are negative values that are less than 0 and values that are greater than a length minus 1. Okay, so if position is less than 0 or position is greater than length minus 1, then we want to throw an exception. Yeah, let's throw a range error. Invalid range is 0 to whatever length minus 1 is. Right. So this is our very simple check. And I'm just going to test this out here. So we have 5 items currently in our list. I'm going to comment this out for now. So if you try to insert at position, and we try to insert at let's insert at position 6, right? This can be whatever. I should expect this to throw an error that we've just described. Yeah, right. It says range error, invalid range. The valid range is between 0 and 4, right? Because the valid range is in a 0 indexed list that we have here. This is 0, 1, 2, 3, 4. So if you're in a certain position, it has to be a position that is already existing, right? Okay, so our check works. And now we can go to implement the actual inserted position logic. Okay. Maybe there are a few things that we also need to take into consideration. If the head is null and you're trying to insert at a position that is not 0, we should also throw an error about this. We should warn about this, right? Actually, let me see if this is going to work. I think it should work with the way this is currently set up. So we have okay. Let's see. The range is negative. -1 is not right. Yeah. Okay. All right. We need to specifically handle for when head is null. So there are 2 ways to do this. We can either assume that since you're trying to insert a new item at whatever position when head is null, we can ignore that position and then insert the new element at position 0, right? Or we can make sure this position is actually 0 when head is null. Otherwise, we complain about it. And I'm more comfortable with the second option, right? Instead of it shows that your API is clear on what it does, rather than being surprising. Yeah, I think the first one adds an element of surprise where a user tries to insert at position 5 when the linked list is empty, and then the list actually inserts at position 0. That's an element of surprise. So when you try to do that, we should reject it. Or when you try to insert at position 0, when the head is null, then that should be acceptable. So and that's all we're going to do. So if head is null, and if head is null, and position equals 0, then we're basically doing insert at beginning, right? So we can call this method instead of rewriting it. Insert at beginning data. Otherwise, we want to complain about something, then return. So this is going to be something like, let's say you can't insert at position when list is empty. I think that's a good error message to throw. And so when we do insert at position 0 this time, it should work. Yeah, it does work. And then if I try to print this list after now, yeah, you see 11 and the length of the list is 1. Let's comment this out. And if I try to insert at position 1, I should get that error that tells me you can't insert at position 1 when list is empty, right? Okay. And this is also in place for when the head is not null. All right, so let's go ahead and implement the actual inserting at position. This has taken the largest amount of time, and rightfully so. All right, so we've handled the position. We have handled the condition for when the head is null, so we don't have to do that anymore. What we have to do now is follow the chain of references, because we have this chain of references that's basically just help us to transverse this entire object or data structure. So we can follow this chain, and in each step we are keeping a count and incrementing that count, and that count is basically the position. So we start at some certain position 0, and we go to the next one, we increment to 1, and we go to the next, we increment to 2. So we keep on incrementing this position until we are at the position that the user is trying to insert this new data at, and then we return the node at that position. Now, when we get the node at that position, what we want to do is do some kind of temporary disconnect. That's wrong. We want to temporarily disconnect, if I can get this to behave. Okay. We want to temporarily disconnect the chain, add a new node in between, and then restore the connection. This is what we want to do, right? So we need to keep track of two references. The reference of the first reference that we're breaking up from, and what is used to point to, right? So that when we are pointing from where we currently are to the new node, we can point from the new node to where we used to point to. So those are two places where we need to keep reference of, right? Okay, so how we do that is back in our code. So I'm going to start from the head, right? And then we're going to need to keep track of what the current node is and what the last one is. That's what I mean by keeping track of two references. The current node would be where we stopped at when we find the node at the position, right? And then the last node would be actually the current node would be when you transverse and you get to the point where you found the position, that's going to be the current node, right? Then you have to point from that current node to the new node, but then you're breaking off current dot next, because current used to point to something before. So what current used to point to before is temporarily going to be stored in another node. So maybe we don't have to keep track of this right here. Yeah, we probably don't have to keep track of it here. Okay. Yeah, this is where we need another while loop. Current dot next. Well, current dot next is not equal to null. We want to set current equals current dot next. But remember, we want to break off okay, so we also have to keep track of a count. Yeah, and count equals 0. We want to break off if this count is position. We want to break out of this loop. And then we increment this count. Right. So whenever we get to this position in our while loop, we would have retrieved the node at that position, and we can then temporarily break the chain of reference from that current node and puts the new node, points the current nodes to the new node, and then points the new node to what used to be the next of this current node, right? So outside here, we want to have the old reference, if you would say. So I'm going to call this old reference of current node. And that's going to be current dot, that's going to be current dot next. This might be null, so I'm just going to make this nullable. It's possibly not going to be null, but well, it could be null if this stops at the end of the list, then yeah, the next node is going to be null, right? So I'm going to be pointing current dot next to our new node, which is breaking off this chain temporarily. And then I'm going to be pointing new node next to the old reference, right? The old reference of the current node. And this is basically inserted position. Yeah, this is inserted position. Okay, so I think that's right. Yeah, that is right. I'm going to go ahead and test this right here using our previous example. We'll print this just before the inserted position. So we should have our list open. So we should have our list 52196. And then when we try to insert at position 1, which is here, what we should have now should be 511 inserted at position 1, then 2196. So let's run this and see. Aha, so it says we are inserting after the position and not before the position. So there's something going on here that is not right. Um, what could that be? What could that be? All current. It's not null if the current count is same as position, then break off. If not, increment the count, reset this to the next node, right? And do the same thing. So this is 1. So now we are at the next node. Oh, okay. I think I get it now. We have to. Yes, I get it now. So we want to be inserting the new node to the next of the parent of this guy. That's the node before current.next. We want to be inserting it at current itself, not current.next. And one way to keep track of that, which is why we have a situation where it feels like you're inserting it after this node instead of before. So one way to keep track of this is you can do position -1, but I think that there will be some interesting edge cases if you do position -1. Another way to keep track of it is have another reference, and I will just call this last. This is going to be I will just set this last to whatever the current is before I set current to next, and then basically here, yeah, here I'll be setting last of next to the new node instead of current to the new node. I think this will fix it. This will fix it. And if we run this now, okay, it does fix it, but it throws off. Let's see. Now I'm just throwing things at this. Okay, now it works. It works perfectly fine. So okay, I see. All right, so I'll go back to using current, right? Okay, no. Uh, okay, yeah. This is current is only necessary for keeping this loop alive. Because it provides us the conditional expression for terminating this loop, which is when the next of this current is null, then we break off, or whatever, if whichever one executes first, if this expression executes first, or this expression, right? So the the change here is that there's a new reference, or yeah, there's a new node that we're keeping track of, which is one step behind of current. So imagine, let's go all the way back. So imagine both of them are first set to the head. So in the first iteration, node A is both current and last. And then in the next iteration, the current becomes current.next, but last is set to whatever current is. Current is still node A, then last becomes is still node A, last is still node A at this point, but current becomes node B. And then when we go over this next chain of reference, last becomes node B, or current becomes node C. So the last is one step behind. And so what that helps us to do is whenever we get to the whenever we get to the position where we are supposed to do the insertion, for example, here we are supposed to do the insertion in B, right? And then the last is A, right? So we're pointing that guy. I am missing things. I'm missing things up and confusing things. Am I not? Yeah, yeah, I am. Give me 1 second to go on a water break. Okay, so yeah, I think the mistake there was a mistake in my explanation of inserted position using the diagram, and that was that when if you're inserting at position 1, for example, 0, 1, would be disconnecting this guy and this guy, which is wrong. That would be for when you're inserting at position 2, right? So if you're inserting at position 1, you basically want the new node to be in position 1 and then move every other thing to the right, down to the right. So if you're inserting at position 1, you are breaking off this place. Every guy from here downward, every node at this point downward is broken off. What used to be position 1 downward is broken off. And which is why the last node here makes sense, because the last node, which is one node behind of current, would be node A. Whenever you get to position 1, the last node will be node A. So you're pointing your new node from your last node, put it at position 1 where it should be. So yeah, this is why, yeah, this is correct, and it works the way it should work right now. I'm going to try more examples of inserting at position. So I'll try to insert this at position. So we have 0, 1, 2, 3, 4, 5. Let's try at position 4. 0, 1, 2, 3, 4. And I will insert 59. Right. This works as intended. Position 4. Okay, so I think that brings us to the end of this. You can add the case for the syntactic sugar for -1, which would do the insertion at the end if if you want to do that. But I won't do that here. Yeah, I think yeah, I'll end it at this note. Or before we do end it, we've just covered all of the insert methods, and we've not talked about op. Maybe that, yeah, okay, that would come in a different video. So in the next video, I'm going to implement the method to pop items from the linked list, and we'll also look at the dreaded, maybe not dreaded, um, reverse linked list. So yeah, you learn how to reverse a linked list in the next one. Thank you for sticking along, and catch you in the next one.